with factorization of semantic similarity matrix, we saw that dense embeddings could represent useful information precisely by following Ludwig Wittgenstein definition of word meaning, that is context co-occurrence of in the same context, and they could be short, and importantly they could be dense, because for deep learning models and actually for other machine learning models, but for deep learning models more importantly, the input needs to be dense. The matrix multiplication operations in a neural network, they work better with dense inputs. So to address that problem, and in general to try to represent words in dense vectors, the following approach has emerged. Approach called word2vec, due to Tomasz Mikolov and co-authors. And of course, we could theoretically obtain word vectors by decomposing word similarity or word context similarity matrix using singular value decomposition. But singular value decomposition is practically cubic in its complexity. Because our matrix, for a non-symmetric matrix, right, for m by n matrix, singular value decomposition, when it is truncated, is m times n square, order of magnitude, in the big O notation. But since m and m are equals, that is nothing but m cube when we use just the words as our context. Okay, so what did Tomasz and colleagues come up with? Dense embedding with word2vec. Let's look at the following problem that may be familiar to you from, or just not a problem, but settings that may be familiar to you from autoencoder. Let's represent our input word as a projection from a sparse space to from a high-dimensional sparse space that is the size of the vocabulary to some say d-dimensional space, and then as a projection back into v-dimensional space. Only this is like an autoencoder, linear autoencoder as well. There are no non-linearities here. Remember where you've seen linear autoencoder already in this class? Yes, in autoencoder representation, linear autoencoder representation of PCA, if you recall. So let's look how two alternative formulations were given, and let's look how they work. But before I go into the details, let's give some settings. So, and the settings is the following. Let's represent each of the words as our 1 and k, one hot encoded vector. So we have zeros almost everywhere, and 1 is at the ordinal, basically the position of word I. This will be our input. Let's represent all of our from 0 to size of the vocabulary -1 vector. Let's represent one hot encoded each word in the dictionary that we have to train. So first, let's consider continuous bag of words encoding. So what continuous bag of words does is simple, despite this confusing figure. What it does, it says, okay, we have embedding matrix, W encoder, and this matrix should be of size, well, let me slightly change my notation so it's a little clearer, just for notation. So it's of size V by D, where cardinality of vocabulary of V is the number of words in our vocabulary, and D is the dimensionality of our embedding space. So if we have a word represented as one hot encoding, let's call it WI. Then we have WE transpose times WI, where WI is that one hot encoded column vector, and then we'll get our embedding. Let's call it V. So bye. Then we have another matrix. So remember, encoder and decoder. So WE, WD. The D, WD has dimensions, well, the same but transposed, D by V. So we take WD transpose, and we want this result to be our prediction that reconstructs a particular word. So continuous bag of words, that's the following. Look at this product. Look at yeah, let's throw Z by cardinality of V. This is our encoder transpose. Encoder transpose is multiplied by a binary matrix W sub I. What it does, it just picks this binary matrix because, well, not only binary, it's one hot encoded. It only picks one column of the encoder matrix transposed, one d-dimensional column. The rest just don't matter, right? This doesn't play any role for this matrix. And we got an embedding. Each word now that was originally represented as one hot encoded vector now is represented by a dense vector. And if we take one word v sub w sub I, and we want to generate or predict w sub j, then we take another matrix. What did we call it? This is embedding v, and we can do v sub I transpose wd. But wd is of course a dense. This is the matrix, this is the vector. It's now a dense matrix, but the result that we want to recreate, and I'm transposing it, it better be binary. When we're predicting one word, one hot encoded, we only want this number to be 1. But notice that what it means is that we only care again about one single column in the decoder. This one single column at the position of our expected output of the word j is what we want to estimate. So we want vi transpose times wj or wd at jth location. Slightly messing up the notation. Let's put it like that. So we want this inner product to be closer to 1 while the rest suppressed. Well, that's when one word is predicted from another. So what continuous bag of words does is looks at all of the context, say we have our text, where is word 1, some preposition, word 2, some longer word, some other preposition. So we scan through our text with a window of size, say 5, and we say, okay, this is our context. Slide this window one word to the right, and you'll get a slightly different context. But this is our context. This is our target word. This is our target word. And continuous bag of words, Sibo, tells us take word 1, 2, 4, and 5, and simultaneously from these words predict the target word 3. The way it translates to the matrix multiplication model is we take our input, which was previously one hot encoded for each word, and just put ones at those 4 positions that, and so on, somewhere there, there's 4 positions that correspond to those 4 words in the dictionary. Then we'll just multiply WE times this matrix that encodes the context, and as you see, equivalently, we just summed together those rows in WE matrix that correspond to embedding of the context words. And from this, we want to reconstruct a binary one hot encoded vector with just one element that is 1. So this can be decomposed into matrix vector multiplication, and it can be also solved by gradient descent if we can define appropriate loss. And in order to define appropriate loss, notice what we're doing here. We have V categories, and we predict only one of them. We want to predict only one of them. And this V categories, the size of the vocabulary, and only one maximum. It should remind you immediately of softmax. For softmax, the output of our prediction, since we know what word we're expecting as the output, that is word J, we compute the value so our output will be our output before softmax. Let's write it here. Will be this is decoder in our notation that we just developed in encoder, and this is our input word. But we already figured out that we don't need to multiply input words independently. We can use one combined vector. That's how Sibo uses it. Uses the input. And also notice that this product can be computed super efficiently because we know where non-zero elements are, and we only use those columns of WE transpose that correspond to those non-zero element, and we just sum those columns. That's it. We don't need to go through this, which could be 10 to the 7 millions of words, right? But then those are a dense vector times dense matrix, where this vector was cheap to compute, but now it's dense vector times dense matrix separation, which is not cheap, which is V times T, element order of V times T complexity multiplications. But once we've done that, we can compute the value of our output in the following way. This value, let's denote it y hat. Our estimate by using softmax will be E to our embedding times the column of WD decoding matrix that corresponds to the word J that we want to predict, and per softmax we do W. Well, actually, this is J because this is embedding. J G. Well, to be precise and not overload the notation. This runs through all of the words. Once we have Y, we can compute our loss. Our loss now is simply cross entropy loss and since we're expecting zeros everywhere, but just at this location, that's it. That's all it is. The problems with Sibo is that we need to compute the sum, to compute the softmax over all of the vocabulary. That's computation intensive. And then when we do backpropagation, when we compute backpropagation, we need another multiplication of the transposed decoder matrix WD with the resulting output vector that we still need to compute, even though the loss is just cross entropy loss. So this board is now has a lot of color and a lot of writing on it, but the essence of the model is very simple. Take a binary vector of all of the words that form the context of a target word. Compute the embedding, even though we write it as a matrix multiplication, but it's nothing but the sum of the corresponding rows of encoder matrix WE. Then you have to do a dense vector matrix multiplication with the decoder matrix, apply softmax, compute cross entropy, and keep optimizing. Looks good and nice, but unfortunately it doesn't work that great in practice, as something else that I will tell you about in a second. One more thing about continuous bag of words Sibo model. Remember, we're started with representing our context as binary one-hot encoded vectors. But what we wanted here in the embedding to be the sum of the resulting embeddings, right? V is of dimension vocabulary times the desired D. Since we want a sum of the desired embeddings here, it's equivalent of all of our context words T minus 2 times E transpose plus WE transpose at T minus 1 plus WE transpose WT plus 1 and plus WT WT plus 2, which in turn is equivalent WE transpose WT minus 2 plus WT minus 1 plus WT plus 1 plus WT plus 2, but each of them is one hot encoded binary vector, which means, wait a second, just take our encoding matrix and multiply it by a single binary vector with ones at the positions corresponding to these words. That is clear, right? And then we have decoder and our prediction. Training via softmax, at least is clear, I hope, and theoretically or possible, right? There is no conceptual difficulties with training a model like that. But wait, the main question that we need to answer is, we started with one hot encoded vectors. We need to produce the dictionary before we had like word cat, corresponds to this vector. Word dog corresponds to another vector. And for each of those, we had, for each of the words in the vocabulary, we had one hot encoded vector with a dimension cardinality of the vocabulary, cardinality of V. After the training, we take our VE, or WE, sorry, the encoder matrix. And the encoder matrix is vocabulary size T, where by the same rule, by this one tells us that corresponding row at corresponding position is now, after training, the dense embedding of the word cat. So for each of the words in the vocabulary, we got a dense embedding. And that's the result of word2vec in Sibo. Skipgram, similarly, we take, after the training, we take WE, the encoding matrix, and use the rows as the encoding. But again, when explaining all of that, I did not at all talk about computational complexity. Skipgram model. Let's first talk about skipgram. And again, we look at word 1, or rather word t minus 2, word t minus 1, the target word t plus 1, and word t plus 2. So we'll look at the context. And now, instead of something that seemed logical, instead of predicting our target from the context words, let's try to predict the context words from the target. So counterintuitively, similarly to before, we have W target represented as one hot encoded word. We multiply this W target by our word embedding matrix or encoder to get the target, two-dimensional target embedding. So just let me change color for consistency. We have WE transpose, W transpose. They're all, okay, let's not use that, they're all vectors. What this is, in fact, because this is just a binary matrix, what this is just pick the row of WE that corresponds to the index of the target word. But then we take W decoder and multiply by the embedding V and reconstruct what we want to reconstruct. We want to reconstruct, again, softmax, but we want probability vectors such that the probabilities that correspond to these four vectors in the context, and we choose our parameter to be 5. which is our context size parameter to be 5, and we want the locations that don't correspond to the words in the context to be minimal, and the ones that correspond to be closer to 1. They can't all be simultaneously closer to 1 because softmax normalizes this probability to sum up to 1, but they can be still maximal probability among all other possible options. And doing stochastic gradient descent using using cross entropy as our loss, we can optimize skip grand model. But this computation and backward computation with backprop through this element, because of the size of the dictionary, which could be a million element or millions of words, is problematic. It's we need to compute order of a million or 10 million operations depending on the size of your vocabulary. Each time we compute a forward pass, that's to compute the softmax, and each time we backprop through this, that's when we compute when we optimize the model with the cross entropy loss. That's kind of sad because it's a nice model and it was found to work better in practice than Sibo, skipgram. Well, but lucky for us, Tomasz and colleagues, they found a way how to simplify the computation and optimize skipgram model dramatically. And this what they found is called negative sampling. Which is a simplified version of noise contrastive estimation. Computational complexity of skipgram is unwieldy for large dictionaries. So we use skipgram with negative sampling as GNS. And skipgram with negative sampling works beautifully. Again, what we use is the observation that because our inputs and output matrix are one-hot encoded or binary for Sibo model, we observe that in computation of the specific values of interest from the input and in the output, we only need corresponding rows and columns of our encoder and decoder matrices. So in order to avoid normalization of softmax with respect to the whole vector of all of the words and vocabulary, here's what Tomasz Mikolov has suggested and proved that it works quite well. Let's take some context, like teaspoon of apricot jam, and the sentence continues. So our target word now is apricot, and the rest of the words are context. So instead of doing Sibo or skipgram, let's take the same model, encoder, decoder, the autoencoder, linear autoencoder type. But now let's pick words from the context, like all the pairs: apricot, teaspoon, apricot, jam, apricot, of apricot, and also let's randomly pick words from vocabulary according to their probabilities of the frequencies in the corpus that are not in the context of the word apricot. So it will be apricot, I don't know, pizza, yummy, apricot, I don't know, Greece, and something random that doesn't happen in the context with the word apricot. And instead of performing all of our predictions, let's formulate the following problem. Let's predict the probability of the target word and the context words. That is, let's predict probability of the target word and the context word of appearing together. And if we can predict this, then we can mathematically, in this binary classification problem, predict the opposite value of probability of target word and context word not appearing together. So what we can do, how can we start? We can use a proxy inner product. We can use embedding of our target word and embedding of our context word. We can use inner product as the proxy of probability. So doesn't that all remind you of logistic regression? Remember how we went through logistic regression in great detail. How can we turn this product into probability? Well, simply and easily we can use logistic regression now. Oops, this is embedding of the target and embedding of the context word. So this is logistic sigmoid. Remember, inner product goes from minus infinity to infinity, and logistic sigmoid turns anything that goes from minus infinity to infinity to something that goes from 0 to 1, just like the probability. And by exclusion, we can compute probability of the negative class 1 minus the probability of the positive class. What negative sampling does now for these probabilities over here, negative probability and positive probability, let's assume our relative to our target, the negative context and positive context are independent. So our likelihood with respect to the parameters that we're optimizing, that is WE and WD, is just a product of the likelihood of individual words, well, of probability, right? For the positives and the negatives of target and context words. So what skip-gram model for word2vec does, it says let's take the log likelihood, and the product will turn into sum, and we'll just separate log of positive probability given target and context words plus the sum of the log of negative probability going through all k negative samples. Negative probability, the condition is there, trust me. That what that will be with the sigmoid function is log of the sigmoid of context word inner product inner product of our target and the context plus the sum. Note what happened here, or what happens here when we have 1 minus when we have 1 minus sigmoid, we'll get sigmoid into negative target transpose context over 1 plus sigmoid, exponent e to the minus target transpose context. Note that this is the same as 1 or 1 plus target transpose context. You can do the algebra and you'll get this. So for the negative samples here, our log will be of sigmoid with negative V transpose and the corresponding ith negative word. So now this is our logistic objective function. We can optimize it by gradient descent. Look what is important. We only, at each step of the gradient descent, we only have k plus 1 vector multiplications. There are no million multiplications per each context. This is for one target and one positive word in the context. We only have k plus 1 times d multiplications because of the complexity of this vector product. So simultaneously, we're only working each iteration and each gradient update. We're only working with one vector, with a few importantly, vector operations. So we selectively update only those products that matter. So before in the full skip-gram model, we were computing softmax and normalizing everything, and in the backward path accounting for that. That was much more optimal in the sense that each iteration was computing the gradient in correct direction. But in this case, we are encouraging the product of the target with the context word to increase, while we're suppressing the product of the target with the out of context or negative sample word. So if we just try to increase the word product with the corresponding word that is in the context, the positive sample, then we wouldn't be able to control, or we wouldn't have been controlling what happens with other samples. Not that they would arbitrarily increase, but that's possible too, but they would increase in an unpredictable manner. But by doing this variant of noise contrastive estimation, we are simultaneously trying to maximize inner product between those samples that we want to be close and minimize inner product between those samples that we don't want to be close. This learning type problem, when the learning focuses on pulling similar samples together and dissimilar samples apart, is also called metric learning. And the key here is to know that even though we constructed a supervised problem, right, we have training data, we know that this word should be close to the target word, we know that this other word should be far from the target word, and we're training it with gradient descent by minimizing the loss here. This is actually not a supervised learning problem because we didn't have to label anything. We framed the problem as a problem with labeled data, but we did not label or we didn't employ any human labelers or any labelers for that matter. We just used the structure of the problem. We used the context in the corpus of the words, which words appear together, which words don't appear together. This type of learning is an emerging field right now, and it's called self-supervised learning field. So word2vec, skip gram with negative sampling, very efficient, implemented in multiple places. So I can recall offhand at least 3. So one is the original word2vec, you can Google it. Another one is Spacey package, very convenient, very simple to use, very fast. And another one is Gensim package, also pretty convenient to use. All in Python, of course. So after we've gotten word vectors, what do we do with them? Well, we can do lots of things and all sorts of things. Interestingly, if we look at word vectors, say man and woman, and subtract one from another, or simply look at the vectors that connect man and woman, uncle and aunt, king and queen, we will find that in word2vec representation, they are collinear and pointing in the same direction. We can also do vector algebra. We can take word vector for king minus word vector for man plus vector for word vector for woman, and we can find the nearest vector in the vocabulary that is near the resulting vector, and it will be queen. We can do similar vector algebra with word2vec vectors. We can take vector for Paris minus vector for France plus vector for Italy, and the nearest vector in to where the result of this vector algebra will be Rome. Amazing and surprising find. We can also look at project some of the vectors, some of the relationship. Again, we see this collinearity. Look, king and queen, emperor and empress, duke, duchess, earl, countess, what is it, nephew, niece, brother, sister, uncle, aunt, man, woman, they all pointing or connecting in the same direction. We can also see some degree, like slow, slower, slowest, their location, and then short, shorter, shortest have similar gamma pattern, strong, stronger, strongest, and others. And this is all just from co-occurrences the inside of Ludwig Wittgenstein looks like was right. There's lots of information, lots of structure in the word context co-occurrences. We can study how that, well, language is a living animal. It evolves and it changes as we change. So we can study with word2vec, we can study changes of the word meaning, excuse me, with the word2vec, because the language is a living animal, it keeps changing with time. We can study the changes in language using word2vec with respect to how the meaning of words was changing, from 1900 to 2000s. Let's look at this. This is based on 30 million books from 1850 to 1990 from Google Book data. Look how the word gay, for example, changes from 1900 to 1950s and 1990s. In 1900s, gay is surrounded by daft, flaunty, tasteful, and then slowly it goes through cheerful, sweet, pleasant, and in 1950s the meaning was bright, witty, what else, and then to the 1990s we get into the bisexual usage of the word gay. That's a quite transition of meaning through just 100 years. Similar stuff, but now caused by different changes in society. Those are more of a humanitarian type changes. The society gets more humanistic, more tolerant, and those are more technologically inspired changes. In 1850, broadcast was to seed, sow, to spread around, to scatter. In the 1900s, it was to circulate newspaper and things like that. And then closer to the 1990s, it's radio, television, broadcast, something that we used to know still. Similar with the word awful, as you know, words awful go through reversal of meaning. So majestic, solemn, dread, it goes to horrible, appalling, terrible, to back to wonderful, weird, and awfully. That's interesting. Simple word context co-occurrence contains such rich information that it's a shame if you're working on your project and not using word vector representation when representing your words. You're losing out on a lot of that structure that the model now doesn't have to learn. It's pre-trained, and the model that you're training for sentiment analysis and for other types of predictions from the text can just jumpstart or warm start from this rich body of information already embedded into the word vectors, instead of trying to learn this starting from just merely convenient placement of words in a vector space that classical bag of words model gives you. So takeaway bits: simple and efficient dense word embedding. Use skip-gram negative sampling unless you know what you're doing. Word2vec gives semantically rich space, even algebra works. And to the point I just made, if you're encoding words as bag of words in your project, you're missing out on a powerful model.